Okay, now we look at the teardown of the iPhone 6. I took the images from a website that you probably know. It's called ifixit.com, and there are many teardowns. It's fun, basically. It's fun to look at all the different teardowns. Okay, so we start from this phone, and then we are going to look at the main components. As you are going to see, there are many different chips with many different functions. Now, okay, if we open it first, you can see there is this large display here, which is of course the display that is on top, and the main things that you can see now is the display, which is in LED display, let's say relatively high definition, but not record high for the industry. The other thing that are pretty clear are the front-facing camera, which is relatively large on this side, on the same side of the display, and then the battery. Okay, the battery is a lithium battery, and of course this number of ampere hours is the capacity of the battery. Also in this case, not a record capacity from the point of view of the industry. This is the let's say basic iPhone 6. Of course the 6 Plus has a much larger battery. Then the main board is this one. It has this L shape because of course you need to make room for the battery. Now this is the top part. Of course from the other side you have the rear facing camera, which is the high quality camera, the so-called eyesight, and then this is the Wi-Fi antenna. There are of course many different antennas on board, because you need to have an antenna for the let's say for the telephone network, then you need to have a Wi-Fi antenna, then you need to have an NFC antenna, because even if they are not very much used, you also have near field communication capabilities on the iPhone. So you need to have at least these 3 antenna, plus you need to have a GPS antenna, and you need to have a Bluetooth antenna. Then it's there are many different, so there are different antennas spread over the main board. The Wi-Fi is here near the top, close to the camera, and also, as we shall see, all the chips related to Wi-Fi transmission and reception are close to the antenna. Of course, always the chips are very close to the radio antenna. Okay, then if you look at the board, as I mentioned before, it's a L-shaped, and you have chips on 2 sides, and of course this the top of the image is the top of the phone, and of course this white rectangle here is the room for the battery. Okay, so let's look at the main point. We are looking at the front, okay, from the top of the phone. Let's just consider the largest chips. Now, this one, let me use laser pointer. Okay, this one, of course, is the microprocessor. Okay, actually, it is a system on a package, because in the same package you have both the microprocessor, which is in a 20 nanometer CMOS technology from TSMC. TSMC is a foundry. It is based in Taiwan. This TSMC stands for Taiwan Semiconductor Manufacturing Corporation. Okay, and it's the largest foundry. A foundry is a fab of silicon chips, which makes chips for third parties. In this case, the design is by Apple. Is the famous A8 processor? So the design is by Apple, but Apple does not manufacture semiconductor chips. The manufacturer is this TSMC corporation. Okay, and this is pretty common in the semiconductor market, since fabricating advanced technology integrated circuit is extremely expensive. There are specialized companies that only fabricate chips. So previously I mentioned Intel, which is a microprocessor company that fabricates its own chips, because Intel has fabs. But for example, many other companies do not have their own fabs. Apple fabricates at TSMC. For example, if we're talking about smartphones, all the Snapdragon chips, microprocessors are by Qualcomm, as you know, but they're not fabricated by Qualcomm. Qualcomm has no factory. They're fabricated again by TSMC mostly. Okay. On the other hand, Samsung has its own fabs. Okay, it really depends a lot, but the number of fabs are really few, and very few companies can allow themselves to have advanced fabrication, advanced technology fabs. So there is this segmentation of the market. Basically, only Intel and Samsung can fabricate their own advanced chips, and all the other companies have to use foundries. Okay, in this case also Apple actually. And I was saying that this is a system on package, because basically you have two slices on silicon. On one slice you have the microprocessor, and on the other slice you have the DRAM. You have a 2 gigabit of DRAM that are used by the microprocessor, and they are in the same package. So, and as you can see, it's the largest piece in the main board. Of course, this is the space for the SIM, so it's not used by chips. And then below you have the part that is used for the cellular network. You can see the legend goes color by color. So this is the Lte Modem, which is made by Qualcomm. You can see that most of the RF things are made by Qualcomm or Skyworks. So these are power amplifier for the low band of LTE by Skyworks, for the high band by Avago, for the ultra high band from Avago again, and for the mid band by Skyworks. So you have a chipset from different companies that are used to include to take care of 3G and 4G communications. Okay, and they are all in these regions. The modem is in the in the baseband. Okay, and we are going to collectively look at that part. It's not, I mean, there are different chips, but more or less just take different band of the LTE spectrum. And then this is an important piece, is the 6-axis gyroscope and accelerometer. This is done by InvenSense. It's an American company. Again, it's a so-called fabless. The fabless company is a company which does not make their own chip. They design them and then make them fabricated at a foundry. So also InvenSense does not have their own fab, as all the other companies mentioned there. So in terms of fabrication, more or less all the chips are made in the same place, which is Taiwan, but in the design is more or less done in the US for all these companies. This InventSense chip is the gyroscope and the accelerometer. Of course, the gyroscope and accelerometer serves to take into account, to, let's say, is a sensor for the position and for the acceleration in 3 directions. When we say a 6-axis gyroscope and accelerometer, it means that we have a 3D accelerometer plus a 3D gyroscope on the same chip. In the previous version of iPhone, this was done by STM. It's a nice story in the sense that you need to know that ST Microelectronics, which is a company that more or less is half French and half Italian, has a big chunk of the market of MEMS, which are those micro mechanical sensors, among which we have accelerometers and gyroscopes. And actually, it's the second largest company in the segment of MEMS. The first one is Bosch, the Dutch one, the German one, and then the second one is STM. And basically, from, if I remember correctly, from the iPhone 5 to the iPhone 6, STM lost a place in the iPhone. So they had the accelerometer and the gyroscope, and they basically have no more. And they have it no more. And this is, for a single company, having a place in the iPhone is extremely important, because typically the cost of the accelerometer is let's say $1 per chip. It's not a really costly integrated circuit, but you have to multiply it for something like 300 million iPhones per year. So being in or being out means a lot. Okay, and among all these companies, there's a real let's say run and a strong competition in order to be in the iPhone. And the iPhone is particularly important because it's just one model, so that if you sell one piece, you have to multiply for the whole production. Okay. So it was a big at the time, the loss of the accelerometer it was a big loss. Actually, the iPhone has 2 pieces, 2 acceleration and position sensors. This is one, and then there is another one at low power, so that they have 2 accelerometers. One high precision, large power consumption, and a second one low precision, small precision but small power consumption. So that typically only the one at small power consumption is used unless you have to run an app, for example a video game, which requires let's say a high definition accelerometer. So of course there's a lot of room on the board for them. Okay, then the other, still looking at the same side, just to have an idea of everything that is contained here. On the same side, we have also other pieces, the smaller pieces. There's the another chip from Qualcomm, the envelope tracking IC. The envelope tracking is a baseband chip for the 3G and 4G communication. All the part related to 3G and 4G communication is here. Also, the orange one is the antenna switch module. The antenna switch module is a module which switches the antenna from the transmitter to the receiver, because you typically have only one antenna, with a time division multiplexing, it is connected to the transmitter or to the receiver, and you need a switch to do that. So this RF micro device module is just the antenna switch. And then there are other power amplifiers, and the green one is the Bosch accelerometer, the low power Bosch accelerometer I mentioned before. So it's close to the InventSense one. They are never on at the same time. Okay, on the rear side, on the back side, you have other stuff, and again, the biggest piece here is the flash. Oops, sorry, the flash memory, the red one. In this case, it is a 6 GB system on package. You should consider that in a flash memory you have more or less 1 transistor per bit. So 6 GB means 128 billion transistors. Okay, because it means 128 billion bits. More or less, you have 1 transistor per bit, and that's the size. So it's not just one chip. In the package, you have more than one chip that contain all this memory. And then there is this second part, is the yellow part. This is the Apple Dialog Power Management IC. This is again, it's not something that Apple does. Basically, is done by a third party, which is Dialog Semiconductor. It's a company based in mostly in UK and in Germany, and they make the power management IC. This is a chip which basically manages the battery and provides all the supply voltages to all the chips. So it is connected to the battery and provides all the voltages to the various chips, and you have to consider that the display and the memory and all the chips and all the radio frequency chips have to use different supply voltages. So this single chip has to provide all the supply voltages. It is one of the expensive parts of a smartphone. And actually, I don't know if you probably know, but in Livorno, close to here, there's a design center of Dialog, and where they basically do these chips, because Apple is the main customer of the company. Of course, they have I think something like 20 design centers around the world, and one of them is here in Livorno. And then we have okay, the touch screen controller, and this NXP NFC modules. This is for the near field communication capability of the smartphone. Is used very little, but it is still there. We will have a look at it. That is basically to be used in order to communicate with passive devices at the distance of a few centimeters, to have functionalities like let's say an electronic wallet or ticketing and similar things. And then okay, in the bottom part, again, you have a transceiver of Qualcomm. Again, all the radio part for cellular phone communications is in the bottom. The part for the Wi-Fi is in the top. You remember probably there was here the antenna, and here you have the Wi-Fi module, which has a complete module with the power amplifier, the transmitter, and the receiver for the Wi-Fi communication. That part is on the top. The Bluetooth chip, I did not see it. Probably it's in the next. And okay, these are smaller things. I only want to mention this part. Oops. This part here below, the Qualcomm Power Management IC. There's another power management below here. There, maybe you can see that here. There's another power management circuit, which essentially supplies the power to all the radio frequency modules, to all the 3G modules, and is done again by Qualcomm. So if you remember, most of the chips for 3G and 4G communication, and also the power supply is done by the same company. Qualcomm is a world leader in that part of integrated circuits. And that's it. So you see there are a few, something like 20 different integrated circuits in the board. The largest of them are the microprocessor with the DRAM and the flash. I don't know if you have probably seen, but in the iPhone 7 the smaller flash is 32 gigabyte. So no, 32 is 128 gigabyte, from 16 to 128. So it's going to be much larger. Of course, the technology has improved. The size is not let's say 8 times this one, but it's still a big chunk of the whole space. Okay, just for curiosity, it's I think it's useful to have a look of the cost of the components and what are the most expensive ones. I mean, this you can take it as a curiosity, but there are some things that one can expect and some things that are unexpected. Of course, you can see here that the display is the most expensive part. The second part is the processor. And then the other part is this BB plus XCR, which is all the radio part. The radio part for the 3G. So 1, 2, and 3. Then the camera. And the power management plus the audio, because they go together. And the audio, it's a smaller part of it. The power management is not small. I mean, it's more or less the total cost for the iPhone is $7 on $240 total in components. Okay, including also assembly test and the mechanical materials. But we are going to look. We are going to look at all the main parts in order to, let's say, understand what are the metrics and what's the main technological issue about them. Okay. We are going to start with the microprocessor, just because first we are going to investigate the logic. I'm going to say just a few things now, and then next time we are going to go into some more quantitative things. So the i8 is a package on package. There is, I'm sorry, I was wrong before. It's a 1 gigabyte DRAM, not gigabit. 1 gigabyte DRAM on the top, and the complete processor on the bottom. Is a 20 nanometer process by TSMC. TSMC had still a planar process, also in 20 nanometer. I showed you before that Intel had a vertical 3D process at 22 nanometers, but TSMC continued up to the 20 nanometer process with a planar process, so traditional, let's say, geometry of transistors. And this is a photo of the die. Of course, you can only see the large areas, but I want just to show you the main parts. So the size of the chip is not that large. It's more or less 1 centimeter by 1 centimeter. Okay, you can see the details here. And there are around 2 billion transistors with 10 levels of metal. So the levels of metals are the levels of metal interconnections that you have between chips. Also, that is increasing, let's say, every few years. Every few years you have an increase of 1 level of metal. Regarding the architecture, you have a dual-core CPU, which is this one below here, with an architecture which is a Cyclone ARM V8, a 64-bit architecture, and you have a quad-core GPU. Okay, these are the cores, and the part in the middle is the shared logic and the logic for interconnections. And the rest of the chip, this part, is the part basically for interconnections with the memory, because you have in the same package the DRAMs, and outside of the package you have the flash. So the interconnects with them takes a large part of everything. This part is the cache. The cache is made with SRAM, with static RAMs, as usual. It's you have 3 levels of cache. This level is shared, and then inside each core you have level 2 and level 1 cache. Just for completeness, this was the and last year was a preview of the iPhone 6s. More or less the space was similar. The technology already changed. It was a FinFET technology, so a 3-gate technology with 16 nanometer equivalent gate length, and a 2-core CPU and a 6-core GPU. So the size of the silicon die is more or less the same. Of course, you have a smaller technology. You can cram more transistors in the same chip and increase the number of cores and the functionality. This is, of course, something that you have noticed. I mean, probably because you follow some aspects of the technology. What typically happens is going from one technology to the next, that you have an increase in the number of cores. This is something which we take for granted, but it is relatively new. It's something from the last, let's say, 8 years. Before, the main thing, before you typically you did not have more cores. You just had faster chips, and there's a reason for this, which is a basic physical reason. Let me stress this aspect by showing you a few figures that to illustrate you the trend. These are not updated figures, but what is important for me here is the trend. Okay, look at the historical evolution of feature size, supply voltage, and power. Okay, this is total power of the chip. Now, the red triangles are the supply voltage. Okay, so in the 80s you had a supply voltage of 5 volts for CMOS technology. Okay, then you can see that in time, chip after chip, you have a reduction. These are different chips in the market. You have a reduction of the supply voltage, and now you typically have a supply voltage which is between 1 and 1.5 volt. Okay, between 1 and 1.5, you have observed a decrease of the supply voltage for the microprocessor, for example. We're talking here of digital chips. Okay, so for example, the microprocessor, we're not focused on that one. This goes more or less in parallel with the reduction of feature size. This is the feature size. So, for example, the gate length. In the 80s, you had 2 micron technology, then 1 micron, then 0.8, then 0.5, then you go here, for example, it stops in 2003, you had the 0.13 technology. So you can see here that the reduction in size more or less is followed by a reduction of the supply voltage. You see, more or less they are parallel trends. And this is what the scaling suggested at that time. So you had a reduction of size, a reduction of the supply voltage. And this would imply an increase of the clock frequency. In the same plot, you can see the power consumption is this blue diamonds here. You see the power consumption is increasing. And of course, this is not something that can continue without any problem. Most of this increase is due to the increase of the chip area. Okay, because the increase of the number of transistors is many orders of magnitude. You have just an increase of a factor 100 here, which is more or less the increase in the die area. So the power per unit area remains constant in the whole in these years, and therefore you just have to use more powerful fans in order to keep the temperature constant. What yeah, let me just I stop with this observation. What happens is that for a reason that we shall see next week, it's not really possible to decrease too much the supply voltage. But if you do not decrease the supply voltage, the problem is that the power consumption increases. And therefore, what you have is this, we will start from this next week, this power panic. This is, let's say, a funny story. There was this ISSCC conference in 2001. Is the most important integrated circuit conference at a global level. There is this vice president of Intel for technology that shows this plot. This is the power density in power per unit area as a function of the production year. And then it says, okay, this is the problem. We have a problem. In the 70s and in the 80s, we could increase the number of transistors per chip, doubling it every 1-2 years without any problem, and keeping the power density constant. Now, we are in this situation. We cannot decrease the voltage supply fast enough, and therefore the power density is increasing. If we continue like that, the power density is going to reach, let's say, intolerable level. This is the level of the nuclear reactor. This is the level of a rocket nozzle. This is the level of the sun surface. So we need to do something. Okay? Now the story is funny because next day Intel stock closed down by 2.8%. It made the news in the newspapers. You can search in the internet the newspapers of the day after. They really made titles with this statement by Intel, and this actually was a huge problem. I mean, they could not control power consumption on a chip. I remember at that time, let's say that we had on the motherboards every year larger fans in order to dissipate heat. And basically between nerds we discussed about what is the best fan, how can I change the fan in order to go faster, right? So and something changed, and actually what changed is the following thing. The industry decided not to increase the clock frequency anymore. At this time it was something like 2 gigahertz, and it was increasing every year, and indeed it did not increase anymore. And from that time, the way to increase the computational capabilities in microprocessors was to stop increasing the frequency and to increase the number of cores. So that choice was due to the intolerable power consumption that an increase in the clock frequency would bring. And indeed, if you look at the power consumption per year, you can see that at some point it saturates. And this saturation is when you start having multiple cores on a single chip. So I'm stopping here. We will look at the quantitative aspects of this thing next time. Let me just stop here. I want to, before letting you go, I want to let me stop here, but I want to tell you something.